Okay, I'm going to go ahead and introduce Dr. Daniel Angerhausen. He is an astrophysicist and astrobiologist at the Institute for Particle Physics and Astrophysics at the Particle Physics of Zurich, the former NASA and Center for Space Habitability Fellow, and is also a founder and CEO and tech communication startup called Explainables, a diverse team of highly qualified young communicators from all over the globe. On his search for planets around other stars, Daniel flew 5 missions on the NASA Airborne Telescope called SOFIA. Daniel's also a mentor and science committee member of the NASA Frontier Development Lab called FDL, an artificial intelligence/machine learning incubator tackling challenges in various fields of space sciences in industry stakeholders such as Google Cloud, NVIDIA, or IBM. I'm going to get this pronunciation wrong, but Daniel plays, I think you just put this in here so I would trip up. Okay, Sepak
Takraw.
An artistic foot volleyball game, and has competed at the World Championships in Southeast Asia. And he's definitely going to have to explain a little bit more about that. But the reason we invited Daniel here today was to talk about machine learning for technosignatures on the moon, and to discuss the LIFE mission, the Large Interferometer for exoplanets. So he'll be talking about both of these things, and hopefully this foot volleyball game that I cannot pronounce. And for more Daniel, I will put his website in the chat, and I'm going to ask everyone to remain muted. Unless, Daniel, do you want people to like raise their hand or unmute to ask a question during, or would you prefer after?
I think from my experience with Zoom, I think the best is to type questions if you have them during the talk, and then we do a full question and answer session in the end when we can also, have everyone on the screen. That's usually the best for a Zoom meeting. Usually in in-person meetings, I'm fine with being interrupted, but I think on Zoom it works best to keep the questions to the end, unless there's something like super, weird that you missed to understand something really important. Then maybe someone can watch the chat and then interrupt me. But
okay,
that works best.
So
and it's also going to be too short or two like shorter talks. So we have 15 minutes each. So we have definitely after 15 minutes time to discuss, I think.
Yes, and we have a new guest right now. This is Bella the cat, and she
I also have cats in my slides. So.
And one more thing, I wanted to open up the floor if there's any announcements. Let's wait just 1 minute, and if you would like to make an announcement, go ahead and unmute now, or type it in the
folks have probably seen, if you're on the community mailing list, that Breakthrough Listen had a couple of papers that came out yesterday, one led by our resident theorist, Dr. Brian Lackey, who has been thinking about other places that life might exist around not sort of the nearby star sample and Earth-like planets, but sort of a broader range of environments. So Brian has a paper on our exotica list, as we're calling it, sort of other places that we might consider looking. And then there was another short paper on analysis of the Kepler-160 system that was led by Karen Perez, who is a former Berkeley SETI summer intern and is now a graduate student at Columbia University. And Karen had a nice short paper, which we just heard this morning has been accepted for publication in research notices of the IAAS. So a couple of results that you might want to check out. Hopefully we'll be seeing some media interest in these stories over the next couple of days as well.
Awesome, thanks, Steve. Maybe we can put links to the press release in the chat if you don't mind.
Yeah, I can do that.
Awesome. Anything else before we begin? All right. With that, Daniel, if you want to go ahead and take over the screen sharing.
Yes, so I hope you can see me, hear me.
Yes, it doesn't look like it's on presenter mode at the moment.
Yeah. Okay, so Julia already introduced me. So I'm at ETH in Zurich at the moment, used to be a NASA and CSH fellow, work for NASA FDL, which I'm also going to be mentioning a bit during my first talk. And as Julia said, I'm also part of the Blue Marble initiative called Explainables, where we do everything science communication related. And as you can see from the image, I'm originally from Germany, and probably also hear from my accent, and actually very close to Neanderthal, which might explain the similarity to that guy. I'm the one on the left side, if you didn't see the difference. Okay, so in my first talk, the first 15 minutes, the first part, I want to talk about machine learning assisted search for technosignatures on the moon. But before I start, I want to tell a quick story about my favorite technosignature on the moon. So, and my favorite technosignature on the moon is actually this little flag here. So this is a solar wind collector experiment. So really just a basic aluminum foil that the astronauts rolled out on the lunar surface, and just to collect the particles and everything that was, you know, coming from the sun, because that was totally unknown at that time. And it was actually one of the first experiments that the astronauts put into the lunar ground, because obviously they wanted to have as much exposure of that experiment as possible. And the cool story about this, or the story why I'm so interested in this thing, is because this is the only experiment that went on the Apollo missions that was not built in the US. It was actually built in Bern, Switzerland. So right here where I'm calling you from, and in the institute that I used to work until a couple of months ago. So basically the first flag that was put on the moon was a Swiss one and not an American one. So this is why this is my favorite technosignature. And we are also super proud here in Switzerland and in Bern particularly, and really celebrated last year, are still celebrating, you know, the 50-year anniversary of the moon landing. And that's why I think it's also a great time, you know, for our topic, for, you know, the search for technosignatures on the moon. And the basic idea really comes from the Apollo mission. So the really basic idea that we had, and that was, you know, not just our new idea, but also proposed in the past, was if we have all these technosignatures that we planted on the moon, so the Apollo landing site, other crash sites, couldn't we just train a neural network to find those technosignatures, to find these, you know, prints, human imprints of the lunar surface, and then use this machine learning algorithm that learned to find the Apollo landing site to see what else it can find on the lunar surface. And that's really the basic idea behind what we're doing. You know, see if you can find other things like crashed Russian or Indian or Israeli spacecraft, or maybe even something that was left behind from a previous human civilization that had an Apollo program billions of years ago. So really the idea to find everything that is anomalous on the lunar surface. Also natural impacts, so there could also be astrophysical phenomena that we could be able to find on the moon. So all this could be part of this machine learning algorithm. And the idea is really not new, so it's not our idea. So it's really based on work by Paul Davis and a student from, I think, 2014, so about, you know, 5-6 years ago, where he suggested to search for lunar artifacts in the moon based on the lunar reconnaissance orbiter data, which brought us really high resolution, 30 to 50 centimeter in some cases resolution imagery of the whole lunar surface. And as you can see here, at that point, he suggested to use either crowdsourcing, so really like Galaxy Zoo or ZT at Home, you know, all these human labeling efforts, you know, to put all the data on a server and have people look at it and manually mark things that they found interesting. Apparently, they even had a small pool of students and faculty to search the NUC images for interesting features. So imagine this poor group of students who had nothing else to do but skimming through moon images for hours and weeks and days maybe. So we thought that this really is something where machine learning can shine, because it's used, you know, it's used a lot on images, and, you know, also can deal with really huge amounts of data, really big. So this is why we got to this. But before I want to go more into the details of the machine learning part, I also want to remind you on this technosignatures axis of merit. So most of you might have heard about it. So what I think for these lunar artifacts is really great is that they are really at the better end of most of these axes. So the search can be done now. So we have the data from the Lunar Reconnaissance Orbiter. We have all these new machine learning technologies. The search is relatively cheap, so we really just need, you know, some high performance computer to run through the data, but it's not, we don't need a dedicated space mission or anything for it. It has many ancillary benefits. So as I mentioned, we can find, you know, crashed human exploration starships. We can find maybe impacts or other anomalies on the moon. These technosignatures should be long-lived. So if, you know, someone put a monolith on the moon, or if, you know, a spacecraft crashed on the moon thousands of years ago, it should be relatively long-lived. It's probably, if we find something and can go there and check it out, it's probably unambiguous. So it's not really a question if eventually to make sure that it's really a technosignature. It doesn't need a lot of extrapolation from Earth 2000 technology. So basically our technology up there is from 1969 and even earlier. So it's not really, doesn't need any extrapolation. And then it's inevitable, detectable, and also obviously very information rich. So if we find, you know, a hard disk in a flying saucer on the moon, that is probably very information rich in comparison to just, you know, a radio signal of some prime numbers from a star that's 10,000 years ago. Not to say that this is also an amazing work to do and exciting work to do, but I think in all of these axes, the search for technosignatures on the moon and also on other bodies in the solar system can be really, at least on these axes, is really interesting to perform. So I actually wanted to do a quick experiment with you, but I don't think that the annotation tool on Zoom is working right now. So this is something we thought about in the very beginning of our experiment, or when we start thinking about it. So, and I think we also brought up this topic of shedding points briefly at the Technosignature meeting in Houston 2 years ago. So what shedding points are, or so-called focal points in game theory, it's a solution that people tend to choose by default in the absence of communication. So think about the time, you know, 10 years ago when you didn't have a cell phone, if you lost your family in the mall. You meet every full hour at the meeting point. Or if you know, were a little kid and you lost your mother in the grocery store, you probably would go to the cashier because you know she's eventually going to show up there or not. So these common denominators, so you know, what frequency would you use if you just have a random radio? So these questions, I think, are really important also if you want to do CT research. And the question we wanted to ask, if you had to choose an area on the moon where you would start looking, which would it be? And I'm not sure if this annotation tool is working. So maybe if some of you are able to use the annotation tool, feel free to make a cross or a heart or, you know, whatever else on the lunar surface where you would start searching. So one could argue, okay, if I was an alien civilization that would really leave a message for us, I would probably put it on this central point in the substellar point, or maybe in the center of a crater where it's really exposed. One could argue maybe the poles are you know, a better chilling point. So I think this is an interesting discussion to have, and feel free, you know, to send me your thoughts. Maybe take a screenshot and then, you know, manually put a cross on area on the moon where you would think that we should start searching. So this is really an interesting experiment, or maybe we make an API, a quick, you know, website where people could put their marks on it. So this is really a one test to check these chilling points, you know, in absence of communication, where would you look? Okay, I want to briefly also mention the framework. So the framework in which we started working on this project, because it's a little bit different from this classical academic collaboration, because the idea was actually started at NASA Frontier Development Lab, or at least the people involved in this project found together through the NASA Frontier Development Lab. As Julia mentioned in the introduction, this is an AI incubator, kind of like a hackathon, organized or partnered by NASA and the SETI Institute and a couple of commercial partners such as Google Cloud, NVIDIA, and other players. And the basic idea is we meet for 8 weeks, or used to meet. This year it's online. We meet at the SETI Institute for 8 weeks. We got specialists, half from the domain sciences, half from machine learning, computer sciences, and solve questions that NASA asked, from planetary defense to solar storm prediction and that kind of stuff. And this is where I met my collaborators. So it's Adam Leslikowski and Valentin Bickel. There, I think both of them are also on the call, and also Michael Hipke, which probably many of you know from a bunch of SETI work. This is my team, or our team that we worked on this project. So Adam works for NVIDIA, so he's really the expert on the machine learning side. Valentin is very experienced in using machine learning algorithm on moon data, so he's really on this interface. Had a really nice paper on in Nature this week, where or last week, where he looked for rockfalls on the moon. So check this out. If you Google his name, rockfall moon, you will find a really interesting paper on similar approach using machine learning to identify rockfalls on the moon. So through this NASA SETI frontier development, we found the right team, hopefully, to solve this question with all these different expertise in computer sciences and as well as in the domain. I don't want to dig too deep into the whole machine learning stuff. So there are better experts here on the call. If you want to hear more details, feel free to contact them, or maybe we can have a quick discussion. I just briefly want to bring up 2 of the techniques that we are currently using and have been testing. So one are deep neural networks. So really these classic neural convolutional networks that are the reason for the main buzz around machine learning at the moment. So many things that we've been using for years, such as, let's say, MCMC, even the principal component analysis, is technically machine learning, but it's really these deep neural networks who made this big wave, this big buzz around machine learning and artificial intelligence in the last couple of years. And another structure that we are using are so-called autoencoder architectures, which is basically the combination of an encoder and a decoder. So you put something in, let's say a spectrum of a star or a planet or whatever, then you reduce it down to way, way less information. So let's say you go from a 2000 point spectrum to just three variables here, and then you blow it up again to an output, and then you iterate that as long as possible until your output looks like your input. And then you basically reduce your input to this, let's say in this case, 3 variables you have in the center here. So it's a little bit like a bottleneck. It's similar to a PCA in the sense that it reduces the dimensions, and you can, whatever you put in the beginning, you can reduce it to 3 or 4 factors, which we call latent variables. And then you can look at the distribution in these latent variables and use that also for anomaly detection. So this is and I hope that not all of the machine learning experts that are listening are like rolling their eyes right now. So please correct me if I was totally off here. And there's probably people to better explain this than me, but just to give you a quick, at least mention of the techniques that we're using, it's mostly deep neural networks and autoencoders that we have been using. 2 problems that we encountered. So you can imagine it's a lot of data, and just downloading the data took a while for us to find the right person. I looked it up. I think at least in the first 2 years, LRO was downloading 130 terabytes of data per year, and just the image data from the NUC and WAC are about 1 petabyte of data. So you can imagine that's nothing that you just download in one afternoon with your old notebook. So just figuring out who to contact at the various archives and where to host 1 petabyte or terabytes of data, this was not really easy for us. We came up with some solutions. So we got a couple of APIs and also a cloud solution that we hopefully can soon share with the community. So we are working with our partners at Google to maybe even provide that data set for everyone as one of the Google provided, Google Cloud provided training data sets, working like a Kaggle challenge or something like that. So stay tuned for that. Another problem is the data imbalance. So we got millions, I think about 2 or 3 million large images of the moon, but really only a few of these technosignatures that we're looking for. And this is always, it's kind of like a standard problem in machine learning. You want to, you know, especially if you do anomaly detection, but you have to kind of like balance your data. So we had a couple of ideas and a couple of solutions how to call what we do data augmentation. And here's the promised kitten pick. So I hope the cats in the audience also feel good to see themselves here. So it's basically what you can see here is we got, if you only have one cat image but want to get more images, you can switch and flip and zoom in, zoom out, and do some sort of transformations with your image, and then artificially blow up, in that case, the images that have the feature that you're looking for. So we have a couple of solutions for that. Also, you know, to get a more balanced data set, or at least make the data set balanced enough that it doesn't bias or distort our training algorithm. And here are our first results. So again, I don't want to go too deep into all the nitty-gritty details. What you should remember is that our algorithm spits out something that we call an anomaly score. So we put in all the data, it analyzes it, and gives us a distribution of the images that we fed it with. And then it assigns an anomaly score. So how, let's say, how far away it is from the median, or some sort of metric for how anomalous that particular image is. And then you can see here, so we trained on an Apollo 17 training data set of about 2,000 images, which had 6 technosignatures in there. And this is a distribution of all the 2,000 images. So you see all these, you know, one big peak with very low anomaly score, like the standard images, and then a long tail with some wiggles here, and then a long tail here. And then all our 6 technosignatures are really here in the tail of the distribution. So the algorithm that we trained really can identify that these are somewhat anomalous images, which is already, you know, great results. So we can have this model that at least identifies, okay, there's something weird with these images. And all of these 6 images are really here in the tail of the distribution and are very in the high anomaly score region. And then we use this model that we trained on the Apollo 17 training data set on a completely new data set. So we took the Apollo 15 data, and this time 8,000 images with 10 signatures, and did the same exercise. So again, we got this anomaly distribution here, like a histogram of, you know, how many images are how anomalous. And again, these 10 technosignatures again showed up here in the tail of the distribution. So really promising first order results. We also were able to publish this at the NeurIPS conference as a little abstract at the NeurIPS, and present at the NeurIPS conference, one of the biggest machine learning conferences. So if you want to read a bit more about the details of this method, I really want to refer you to this paper, where we do obviously put a little more details on how we get there. But take home message here is we got this engine running that can give us this distribution and can identify which images in the distribution are somewhat anomalous. And our next step is obviously to scale this up. So we really want to scale this up, not just in these little patches around the Apollo landing sites, but in the best case to the whole lunar surface, to all the imagery that is available with the Lunar Reconnaissance Orbit. And as I mentioned, you know, this is, you know, terabytes, if not petabytes of data, which we cannot store on our, you know, home computer. And if you want to run these machine learning algorithms, it's also nothing that, you know, your standard gaming graphic card can do. So you really need big computers. Luckily, we already won a little grant from the Google Cloud Education Program. So we got at least something to start, somewhat scaled up version, maybe not like the full lunar surface, but we have some support from the Google Cloud platform to do a first, you know, scaled up prototype to look at way more images. So please stay tuned. So hopefully we'll be finding some other technosignatures, or at least can publish a catalog of orders to magnitude, boiled down set of interesting images, which we then could maybe go through by hand. And maybe at the next IAA SETI talk in 2021, I can already present you the monolith that we found on the moon. And with that, I think I stop for this part, and we can have a discussion about this.
Great. There was a question in the chat. and check your chat, your private chat.
Okay, wow.
If you want, I can read you the question if that would be helpful.
Those focal points that you allude to, there's a special place on the moon because it co-rotates with Earth. There's a spot on the moon surface where Earth is always at the zenith. Okay, that's interesting, yeah. You should look at that one. Oh yeah, then Valentin linked that paper that I mentioned about the rock falls. So I really recommend this. It's also for like, if you're not an expert neither in the moon nor in machine learning, it's a really nice read. So definitely recommend to check this out. Oh yeah, Julia made a poll. Yeah, be sweet. Yeah, and then we got the link for the paper. So any other questions? Did I miss something?
I have a question.
Yes.
So you mentioned crash sites from Russian lunar exploration program, and there are also landed missions, and they're still on the moon.
Yep.
They are large enough to be visible. Did you find those?
They are in our training data. So we got the Lunocode and all these landing sites. So we basically have a archive of all known lunar landing sites. I think Luna 7. I'm not sure about it, but I think there's still one Russian mission that is still missing, and no one knows where it is. So this is kind of like our. That's kind of like our secret or not so secret goal to find that. Something else we also want to test is to see if we can find the Vikram, like the recent Indian crash site, because there we took a couple of days to find it. So this might also be like a commercial or at least like practical application of our algorithm to see if something like that, and hopefully not, but in the future with more traffic on the moon, it might unfortunately happen. So maybe use this algorithm also to improve our detection of these crash sites. So this might at least be like a demonstration of our technique.
Yeah, that's great. What about those rovers? They should leave some traces. Do you see those from rovers?
Yeah. So maybe also Adam and Valentin can chime in, but the tracks. So I think you've seen that in some of the. So you can identify the tracks of the lunar rovers and also the lunar mobile they took up there. So those are definitely part of the lunar technosignatures. I mean, there might be you could maybe mix them up with these rock faults that Valentin was looking for, but in principle they also count as anomalies. And that's the cool thing about this algorithm. It's really kind of agnostic, right? It doesn't exclude, it doesn't just look for square metal things. It really just looks what is anomalous on the moon, right? So this is the cool thing. So there might be even like just strange rocks in this tail end of the distribution, right?
Yeah, thank you. Great talk.
So Svetlana, just I guess address some of the questions you had. So this is Adam. So with the Soviet lander, we basically centered our search around the Apollo 15, 17, respectively, landing sites. And so we didn't find the Soviet landing sites kind of in our stage 2, stage 3 projects, whereas this was stage 1. We want to look for some of the other landing sites. So I guess stay tuned. We didn't look for it, essentially because we looked at patches roughly a few kilometers from the known landing sites. And for the trails, that's an interesting question. We didn't directly look to see in the anomalous images whether those showed up. We essentially just labeled positive samples as ones that had at least 50% overlap with the lunar lander module, which is kind of the largest one, at least in our pilot study. But it'd be interesting to see how much of anomalies for, say, kind of secondary characteristics like kind of rover trails or smaller features would have.
Very cool. Thanks.
Okay, there are more questions online. So Jason asked, how fast does the regolith on the moon grow? This and gardening will slowly destroy buried technosignatures. What is your time horizon? Will you put upper limits on the size of things that you be sensitive to at the end, or does this use of machine learning make that difficult? Have you thought about injection recovery experiments? Okay. As for how fast the regoliths on the moon grow, that's an interesting question. I tried to look that up, and there are all kinds of between 80,000 and a billion years. So maybe Valentin knows more about that. He's our moon expert. Can you say something about this? I'm not sure if he's there. Oh yeah, there he is.
So I'm not entirely sure, but this will be the order of millimeters per millions of years. So it's very slow. So okay. I guess covering like a big object would take a rather long time, I would say.
Mm-hmm. Okay, then put upper limits on the size of things to be sensitive at the end. I mean, I think, and then again, Adam can weigh in. I think it's mostly limited by the resolution. So the resolution of LRO data is about 30 to 50 centimeters, maybe a meter per pixel. And let's say a feature needs at least 2 to 3 pixels. So everything on the order of a meter probably should be in there. What do you think, Adam?
Yeah, that sounds right. I think the limiting factor is going to be the resolution of the imaging data. So the anomaly scores itself, just to dive a little bit into the details, essentially the MSE, so the mean squared error of the reconstruction loss. So you put an image, get something out, compare it to the input. So it's a reconstruction loss that we're measuring in the anomaly score. And really for features on the scale of 2 pixels, or even 1 pixel, if there's a huge discrepancy between the input and the output, that could really drive a high anomaly score to find it. And that's super pertinent, not so much for the lunar lander module, which is on the order of, say, 10 pixels square, but for something like Vikram, if you look at the images, I briefly looked at them, it's essentially 1 bright pixel. So hopefully on the scale of 1 pixel. And if the imaging gets better, then this technique should scale to that.
I guess what I'm asking is, like, let's say you don't find any things that look particularly anomalous, although I'm sure you will, because when you look for anomalies, you find them. But let's say you don't find anything. You say, okay, our resolution was this, so anything larger than this could have triggered our detector. But in order to put an upper limit and say we can rule out technosignatures of a certain size, you have to know what you would have triggered on and what you wouldn't have triggered on. So I'm asking how you translate this search from just, oh, we didn't find anything, into there are no technosignatures bigger than, or having some quality that we would have noticed.
Interesting. Yeah, so I guess I would say I wouldn't be comfortable with saying, since we didn't find anything, there's nothing there. I think the Apollo landing sites and some of the other human landing sites are sort of natural injection recovery experiments. If we can't find those, then we wouldn't have that much faith in our model. But if we do find those, say we recover most or all of them in the optimistic case, and we don't find anything else, then at least we can say, as far as the method goes, we couldn't find anything anomalous.
But isn't that also your training set? I mean, you have to find your training set, right?
So the training set was 1 set of landing images, so it was Apollo 17, and then and then the test set was Apollo 15. And so that's absolutely right that maybe there's a difference between the thing we train on and the things we want to find, which are so much more different than the actual training set that we'll miss them. I mean, that's definitely a limitation of this study.
And then my question about the regolith, if you gave the Apollo sites 1 million years and you covered all the tracks with, 1 millimeter of regolith and all of the artifacts with 1 millimeter of regolith, and then you gardened them with the, micrometeorites for 1 million years, do we know what they're going to look like? Are they still detectable?
I personally don't know. Maybe Valentin or Daniel. I guess we can say with confidence what 10 or 50 years looks like, but 1 million years, who knows?
I mean, if this number, 1 millimeter per year, then, how tall is the stage that is left on the moon? 2 meters, 3 meters? So.
But you don't have to bury it necessarily. If you just make it exactly the same color as the regolith underneath, I don't know. I really don't know the answer.
I mean, to the other question, I think my answer would be similar to Adam. So we have this. I mean, we have to maybe think about some Bayesian framework or some metric to introduce to really get an upper limit or something. But at least intuitively, if we can find all the known sites, if we find agnostically find all the Apollo landing sites and all the other landers we know of, then I would be pretty confident that we haven't missed much of a similar size. And one thing that I want to make sure that everyone got, because that is a little bit misleading, because usually people think you need to train a machine learning algorithm and then you can't really use that training set anymore. But what we did here was not like training it to find something like the Apollo landing site. We really had the algorithm look at all the data and find the anomalous data, right? So that doesn't mean you burn the landing sites or anything. So really just, you might end up with, instead of 1 million images with 10,000, that it scores high in anomaly. But it doesn't mean that we are kind of like training it to find what we put in, if you know what I mean, right? So that's different from training a neural network to identify cats. It's basically giving it random pictures and see what is weird, right? So this is slightly different from what we are doing when we do anomaly detection.
Can I seek a clarification from Jason on your question? Are you really getting at the idea that this approach to searching for technosignatures won't find very old technosignatures?
No, I'm not. I think this is a great project, and I'm glad it's being done. I think this is exactly the right thing to do. My question is, what is the time horizon? So if something landed on the moon 10 million years ago, that's a blink of a cosmic eye, and it's totally plausible something could be there. But after 10 million years of micrometeorites and regolith growth, I don't know what that looks like.
I mean, one could probably look at impacts on the moon, and if, I don't know, like a chondrite impacted, and see if it's still black after 1 million years or something like that. I mean, that should be, at least give you a ballpark.
Right. I'm not sure what we're grabbing on with these images and how much of the things that we're grabbing on persist. And it could be they persist for 1 billion years, in which case that's our time horizon. But I think it would be very valuable to know what that time horizon is, or to have an estimate of it. Because I don't know, it could be 1 billion years, I don't know.
Indeed. So maybe one interesting example that I found in the experiments was that some of the other high anomaly score images were images, I think it was from the lunar highlands, where there was a lot of contrast between light and dark, so alternating light and dark features. And the reason that had quite a high anomaly score was that they were sort of alternating very dark, very light pixels, and in the reconstruction that was not well captured. So there were some patterns there not well captured in the reconstruction. And I guess these patches themselves were, on the order of billions of years old. And so what it's latching onto is essentially a failure for the model to reconstruct the input image. And the input image, kind of over many training examples, is trying to reconstruct what it sees as sort of natural or average over all the training examples. So it tries to do a good job on most of the training examples. And kind of the idea of the data-driven anomaly detection is that in trying to reconstruct most of the examples, the ones that look different than the others, they're just the model fails to optimize to reconstruct those. So maybe, just to answer your question, there can be old things which can be failed to reconstruct well and hence have a high anomaly score. Those are natural, of course, as far as we know, kind of highland images with a lot of dark and light pixels. It's really hard to say, we don't have an injection study of something 1 billion years old, as far as we know. So maybe that example is helpful to think about what this method is latching onto.
Cool. So I think most of the other questions in the chat are all more or less about the scale. So again, the scale is between 30 centimeters and like 1 meter per pixel. So this is roughly the type of features that we can see. So footprints themselves we can't resolve, but footpaths we can. We might even be able to check the directions of the paths, I guess. So that means, and again, we need maybe 2 or 3 pixels to actually have a feature. Could you utilize bistatic radar maps images in addition to your other data set? Would this allow to identify buried artifacts since radar penetrates the surface? Technically, yes, but I think it doesn't have the spatial resolution. Is that true, Valentin? I think the optical LRO data is like the highest resolution, right? Or everything else is more on bigger spatial scales, right?
Yeah, so we have radar data, but resolution is bad, and the coverage is also not complete. That's the two main reasons.
I mean, it would be awesome. We actually have another program where we try to fuse data from different wavelengths and find different sorts of anomalies just by looking at different data, but then on bigger scales, you know, anomalous craters or anomalous, you know, geological features rather than technosignatures. So maybe we could add it in a future edition and see, you know, but I think the resolution itself might be not good enough yet. Maybe if we get, you know, the next generation of stuff in orbit around the moon, we could use that data.
I saw a question from Hector, I guess, about spatial scales and whether the network needs to work with particular fields of view or resolution. So I guess spatial scales, it's kind of essentially trained on patches that are 64 by 64 pixels. And with this data, that's anywhere from about 30 meters square to about 60 meters square. So think like half a football field, half a soccer pitch. So that's kind of this upper limit of the size scale down to essentially single pixel differences. So something like a meter scale. And at least for this stage, we just trained it on that 64 by 64 pixel resolution using images that are between half a meter and a meter per pixel. So that's kind of the scale resolution that we have. And I guess I saw one question about, further directions. That's definitely one of the further directions, is to try to scale, to have it train on multiple image scales. And that's not too crazy to think. A lot of kind of recent work in neural networks is that neural networks can do a lot of things at once. So not just, there's a whole lot of work in computer vision on how to make sort of feature pyramid networks as one example, but kind of how to incorporate different scales of image resolutions into network predictions. And not just that, but things like multimodal. So you can combine, for instance, kind of image plus voice plus audio data into one network, and it seems to not get mixed up or confused about it. So I don't really see it to be a problem, but that's definitely further work in order to try to do multi-scale resolution for this kind of project. In terms of number of images, so kind of the target data set that we have is around 50 terabytes total. So that's one coverage of the moon, or kind of most of the moon at least. So 50 terabytes, that's going to be 5 times 10 to the 13. And if you think about a byte per pixel, so that's about 50 billion pixels. So it's a lot of pixels. It takes a lot of computation, a lot of storage. So I would say, I would just stress that most of the bulk of this problem has been and will be kind of engineering problems, software engineering, data engineering problems, that how do we handle this vast amount of data that we have and train in an efficient way.
Yeah, so I think let's just continue. I think this is a great conversation, so we can just continue this, and then I talk about the live mission at the next opportunity. So I wasn't sure about how interested people would be, so I'm fine with just keeping it to the lunar technosignature stuff today, and then make another one about the live, if that's okay with everyone and Julia.
That sounds good. Thanks, Daniel.
And you don't have to look for a speaker for another opportunity, so you got. That should also be done. Okay, Jill is asking, could you do this with Mascon data from the Grace SC? So I'm not familiar. Can you briefly explain, or does Valentina, do you know what that is?
Yeah. So I think, Jill, you mean the GRAIL? So gravity data?
Yeah, but the Grace and Grace FO and GRAIL, pairs of spacecraft that gave you basically the gravitational density of the down-looking piece of the moon that you were going over. So the thing is, could you find buried artifacts this way?
So I think that's a great idea. I would assume that the resolution is reduced compared to the NAC image we have, so half a meter per pixel. But probably if you're looking for very large objects, large and heavy objects, like impactors, for example, that would work, yeah, I guess. Not an expert for that, though.
Neither am I, which is why I asked you.
Yeah, but it's definitely on our agenda. I mean, we have so many ideas, but one would also be to extend it to other data in the solar system. So there's the MRO data, the Mars Reconnaissance Orbiter, which is basically, I think, even better resolution, slightly better resolution. So we could do the whole exercise on the Martian surface too, maybe. You know, we have less landers there yet, and it's maybe more features. It might be more tricky, but in principle, we could do the same exercise for Mars data. Maybe, you know, I'm not sure if the resolution for other objects are big enough, but maybe the next Venus mission, or if something goes, maybe Bepi Colombo for Mercury. So, but let's do it step by step. Start with, you know, we have plenty of work and plenty of data with this optical lunar data, but I think this MASCON is something we should definitely look into. So there was a question by David: how does the actual ratio of technosignatures versus no technosignatures affect the result? So this is what I tried to explain. I think maybe Adam can weigh in on this too. So it's really an agnostic search. So we don't teach it to find Apollo landing sites. We really just ask the algorithm which images do look weird to you. So this is why it doesn't really matter how many, as long as our algorithm shows us that all the ones that we're interested in fall into this tail of the distribution. Then we still have to look at all the images in the tail, but that's still orders of magnitude less than the whole data set. So in terms, we don't really need many of them. So this is kind of like circumventing this data imbalance problem. Is that right, Adam?
Yeah, indeed. And just so I can add to that particular question is why there were more images in the test set. Essentially, we had more positive examples in the test set in order to make the results on the test set more statistically significant. So there's no test statistic that we have. There's no kind of number that we can test and get p-values for. But we really want to increase our confidence that if we put more positive examples in the test set, and if it's finding all those positive examples, the method is somewhat robust, or we have increasingly high levels of confidence that it's robust. And I guess I would, you know, just reiterate that there's kind of no labeled examples going into the training. And in the test set, kind of the way the labels are used are just for validation. So it's just to basically metric how effective the model is in retrieving things that we know and care about. So at those 10 examples that we have in the test set, those don't go into the training at all, into the model. And in fact, in the validation set, those 6 examples that we had don't go in the training explicitly. The only way that they're used, sort of the only way we have label leakage into our training, is through network architecture search, which is kind of, let's say, a weak kind of hyperparameter leakage. So kind of in machine learning in general, you want to measure how well you're generalizing to unseen data. Well, kind of all the data in our case is seen, but we can simulate that by producing these kind of very strong firewalls between our labeled examples and stuff we want to test on, and our training examples, the stuff that we train on. And so I guess I would stress that we try to be mindful of how much leakage there is of labels into our training procedure. So there's some labels that we use in order to tune our hyperparameters for training, so network architecture and training. But those 10 examples were essentially used to boost our confidence that the model is actually picking up everything that we want it to. So that's just a long-winded way of saying that we really just want to be able to make sure that the model is picking up things that we want it to pick up, namely human technosignatures on the order of 10 to 50 years.
And how about the second part? How do you guard against like a false negative, or if you find 10, are you sure you found all 10 and there's only 10 and there's not like an 11th one that slipped through the net or something? How do you quantify
so this
that?
is basically, we wanted to, so there are these 2 metrics, precision and recall in machine learning, and we wanted to get the full recall, right? So we don't want to miss any of these super precious potential technosignatures. We really optimize the precision at total recall. So our first rule is we don't want to miss any, and even at the price of getting a bigger set to look through manually, if that makes sense. So we optimize to get everything in the tail of the distribution, even if the tail grows. Is that a good explanation, Adam? Again, please weigh in, help.
Yeah, and I guess just from the import of the question, I guess, how do we maybe know that we didn't miss anything? I guess, is that we have very good longitude lunar coordinates of the lunar module. So we can kind of very explicitly label that each of the image patches either contains or doesn't contain lunar module images. Maybe there is some other technosignature just happens to be in that patches of images that we looked for. So that's not going to be picked up in the experiment, but we thought that that was kind of a vanishingly low probability that there just happened to be some other technosignature there in the images that we looked. But really, kind of again in machine learning, the model is going to pick up on whatever your labels are, and it's definitely a valid question to ask how valid are the labels, because if you feed in it the wrong labels, it's going to do a very good job of matching those labels, even if those labels aren't very good. So we try to guard against that and try to have our labels, using the most kind of up-to-date lunar coordinates for the lunar module landing sites. So that's how we at least decided our positives versus false positives. And I guess you asked a question about, false negatives. Maybe do you want to say more about that, or what the concern was?
Well,
or
I guess a false negative is just another example of a missed technosignature, like something that was not detected that is a valid technosignature kind of thing. And
Indeed.
I guess it sounds like you have very high confidence that you see everything, you detect everything that is there, and you detect some things that aren't technosignatures. But what about, I guess, are there things that would not be detected that you would, excuse me, you would not count as a technosignature? Like if you find 100 things, do you know there's not 101 things?
I think this goes back to the, or similar to the question that Jason asked, is there any metric? So I think first order, we don't really can quantify what we missed, these known unknowns and things we don't know that we don't know. But at least again, if we find all the known places, I think that's really the only test, the only ground truth we have to check against, right? I don't see any other way to get a metric on this, or to get any other confidence in that we didn't miss much. What do you think, Adam?
That's right. I don't really know how to quantify sort of us missing unknowns.
I guess there's like if you're observing something astronomically, you have this sort of like, well, we were sensitive to this level of intensity, and objects below that level of intensity we would not have seen. So is there anything like, well, we detected these things, but there are other classes of things we might not have detected because our algorithm isn't sensitive to this, or statistically we know we're detecting about 80% of all the things that are out there, but there's still some other things that are not being detected potentially, and how can you quantify that at all?
Indeed. So I think that's a great question, and I think it's definitely a limitation of current machine learning, deep learning models. This whole idea of uncertainty quantification, maybe putting priors on your weights and trying to propagate uncertainty into uncertainty on the outputs, or maybe doing some kind of Bayesian analysis where you get uncertainties and not just point predictions. It's still very much an area of active research in machine learning. We didn't apply any of that to this. So there's no kind of notion of kind of uncertainties, and there's also no notion of sort of, I guess, in traditional signal processing astrophysics, we have some notion that we've characterized all the signals below this threshold or above this signal noise threshold. We definitely don't have that here. It's really just we have these known positive samples. We want to try to find how can we basically return all those, and what's kind of our precision once we return all those. So it's very much, I would say, we don't have either those uncertainty or statistical guarantees, at least yet. It'd be interesting to explore, but I think it really is going to rely on just kind of more fundamental advances in how we quantify uncertainty in these deep neural networks. So I guess again, in general, in machine learning, there's a trade-off. It's not a hard trade-off, but it's somewhat of a trade-off between performant models and interpretable models. So on the one hand, you have performant models like deep neural networks. They're not very interpretable. You don't know what they're doing in general, at least for the most part nowadays. On the other hand, you have machine learning models, say linear regression, super interpretable. You know what's going on. If you perturb the input values in one small direction, you have a good idea about how the output values are going to be changed. but they're just not that performant. So we definitely leaned as a design decision on performant versus interpretable.
I think this is also like a common pitfall that, you know, when people start thinking about machine learning. So yeah, it's not 100% perfect, and we can't really get a metric on false positives, but you always have to compare it to your benchmark, right? So what is your alternative? Your alternative would be like an armada of grad students going through images, or a Galaxy Zoo kind of like platform where people, you know, take images manually, and you wouldn't get any metric in this way either, right? Yeah. So this is an intrinsic problem. That's intrinsic to the problem, not to the method. That's what I'm trying to say.
I think there is a way around
stuff too.
Sorry to interrupt. You can think about injection recovery. It would be a lot of work. I'm not sure it would work, but you could imagine injecting artificial technosignatures into your data set and seeing if you get them back. So imagine what a monolith would look like, synthesize that, alter the data, and see if you find the monolith.
Indeed.
So that kind of injection recovery with artificial signals is common in studies of upper limits in astronomy.
Indeed. I think that makes a lot of sense in a lot of contexts in astronomy as far as I've seen. I think it's an interesting example or an interesting direction. I'd be a bit worried in the sense that we really don't know why machine learning models get the outputs they do, other than just they classify right. So kind of the classic example is that even in a 2-class detection problem for deep neural networks, the probability is just not well calibrated. So when the output of a softmax says 0.8, in general, it's not right 0.8% of the time. So there's post hoc calibration processes that can go on, but those are mostly post hoc. There's some work that tries to make it so that built into the network training, you get those well-calibrated probability models, but that's still kind of very much work in progress. So I'd be worried if you take the simulated data, it'd be interesting to try, but I'd be worried that the model would see the simulated data as an outlier, just in fact of just qua it being simulated data rather than it being technosignature. It'd be interesting to try. I don't know, I haven't run the experiment. It'd be interesting to try, but that'd be definitely kind of first order of worry, is that it's picking up anomaly in lieu of the fact that it's injected rather than that it's technosignature.
Right, and Jason, it would make a huge amount of difference whether your monolith were black or white or gray, and so, you know, the nature of whatever you put in there is gonna skew things.
Honestly, I think in practice, the problem is going to be that we still have plenty of images to go. I mean, you saw the distributions of the tail, and there were still, you know, like hundreds, if not thousands, of images in the tail. So I'd rather be concerned about that we still have to manually look through a bunch of images than that we miss something. But that's really just, you know, gut feeling looking at these images and the distributions.
Yeah, I guess I would stress too, this kind of is meant as maybe an augmentation of kind of human intelligence, in the sense that kind of our precision at total recall, one of the metrics that we explain in the paper, is essentially if you cut it off, the anomaly scores at getting 100% recall, so all the things that we looked at as positive samples, what's the improved precision? And in our case, it's about 50 times. So if you know where the cutoff is and send it off to students or postdocs or even faculty to look at, what's the improved search rate? And it's still, you know, we still get negative examples that pop up in there. So it's not a perfect method by any means, but we can quantify the ratio of improvement, and it's about 50 in our case. So kind of 50 times greater density of positive examples with this method than if you're just doing naively by looking, kind of randomly sampling on the lunar surface. I guess I see Julia, about 2 minutes left.
So if we can, hold any future questions just in lieu of time. I don't want to keep anyone from their next Zoom meeting that they may have. But maybe before we leave, I have 2 polls I want to get out there. Daniel, do you want to put up the picture of the moon?
Yes, let me see, where are we?
Also, we might need some machine learning to differentiate your shirt from your moon background right now, because you're very, very camouflaged. And yes, let's thank our speakers before everyone has to leave. Thank you so much, Daniel and Adam, for jumping in. So let's see if this works.
Yeah, I wasn't expecting to talk this much, but I guess there were a lot of great questions and a lot of great discussions. So happy to contribute.
Yeah, same here. I'm really happy about the discussion. So as I said, I was expecting less discussion and more time for the other talk, or I wasn't sure, how much people are interested. So I'm happy to, talk the other stuff next time.
All right. Give this poll another few seconds. Get your answers in. Wow, it's kind of split across the board.
Oh man, that doesn't help us at all.
Bad for technosignatures.
Right?
Region.
Speaking of.
Okay, I'm gonna go ahead and end the poll.
Okay, let's go for the dark smooth area.
Does anyone have an explanation of why you would look at the poles? Because they're extremely tough on technology. They're very cold and not sunlit. So they'll be mostly in shadow.
I mean, it depends on what story you put in it. You could argue that's where the water is. So if you had built a lunar base, you probably would go where the water is. So I think that there might be a story you can put on every point on the moon why you would go there, but it's still an interesting one, I guess.
I might remark that we know there are a lot of things that have crashed from close lunar orbit, or the upper stages of the Apollo missions that got back into orbit or left there. And I heard from a friend at NASA that several from tidal effects have hit the moon. So if you can find those, that would be a test.
Yep.
And you know the plane of the orbit.
Go ahead, sorry.
You know the plane of the orbit. So you could look along that track, narrow down the search.
Yeah, there was that one probe they crashed on purpose, right? To look for water jets shooting up.
Yeah.
Right. Yeah.
So we have a catalog of all the known artificial things. So that includes, upper stages or any kind of stages that drop. If the position is known, we have that part of our, testing set, ground truth set, whatever you want to call it.
But some we don't know.
Yeah, and those that we don't know, that would be a great, that would maybe also something that could help our metrics. So if we find this missing Russian craft, if we can find Vikram, if we, find stages that no one has seen before, that would be actually also like, again, not a quantitative test, but at least a qualitative test, how good we are at finding these things, right?
In terms of real astronomy, you could think that if you look for just long linear features, you'll probably turn up a bunch of collapsed lava tubes and boulders that are running down slopes that are left track. You can at least get some information out of that and maybe fold it back in and use it to eliminate such cases, even with an AI. You need the topo information. If you want to show that boulder was running down the slope, you really need to know the elevation.
That's actually Valentin's paper, so you should check his Rockford paper from last
that's
week.
right. I haven't seen it yet.
Yeah. So that does a lot of this real astronomy.
I've long wondered how many lava tubes there are we can see.
So I think we found like 200 so far, like skylights, and counting. But there might be many more than that, actually.
Of course, if you're looking for alien artifacts, it makes much more sense to look at our side of the moon. Even though a friend of mine, Kevin Long, has turned up an interesting long signature on the other side, it might be a boulder track. I think he's been in touch with you, hasn't he?
Okay, and we also just found the explanation why most of you turned off their videos, because many of you hadn't had a haircut in a long time.
All right.
I want to ask the people who had 2 weeks as their poll result, where does one get a haircut nowadays?
Maybe it's self-haircut or family.
I did it 2 weeks ago. In Germany, it's open already.
And in
So
Laguna
come
Beach.
to Germany to make hair care. Okay.
There are YouTube videos how to cut your own hair. Highly recommended.
Yes.
Maybe I'll just leave one closing thought about ML for technosignatures. So I guess just from Daniel, since I'm not at all a SETI expert or even astronomy, strong background, I guess there's been a concern in the SETI community about potential human biases in the search for this kind of data. I think, you know, one of the big promises of ML is that ML does things and, you know, it does things that humans do, but in a way that can be much different. So for instance, for images, it picks up on patches and textures in ways that really kind of human cognition doesn't. So it can be fooled. So machine learning techniques for computer vision can be fooled in ways that humans aren't usually fooled. Humans can be fooled in ways that machine learning techniques aren't for computer vision. So machines see the world in different ways than we do. Also qualitatively, in some of the ML systems that are trained for, say, chess or Go, at least the people who play these systems say, you know, they have strategies that they've described as different or even alien. And so I think it definitely be worth taking this kind of broad variety of approaches, short of, say, asking, I don't know, dolphins and octopuses here, you know, as examples of different kinds of intelligence for us to look for, say, these technosignatures. I think ML definitely has the potential to broaden and kind of diversify the way that we look for these signatures. So at least that's the hope for this kind of approach.
All right, well, thank you everyone for joining, and thank you again to our speakers. This was great. It was really great to see faces. And I'll send around information for the next one and hopefully the recording soon. And thank you again, Daniel and Adam, for jumping in and for the great discussion from all of our guests. And we'll see you next month. And be safe. Well.
Thanks, everyone. Thanks, Julia, for organizing. Thanks, Daniel.
Thanks. Cheers.
Thanks.
Thanks,
Bye-bye.
Lizzie.
Bye.
Bye-bye.
Cheers.